Hi guys, so today we're going to take a look at question 7 of the 2016 exam paper 2. So a glass roof lantern in the shape of a pyramid has a rectangular base CDEF and its apex, its point, is at B. The vertical height of the pyramid is AB, where A is the point of intersection of the diagonals of the base as shown in the diagram. So A is just the center point of the rectangle. The length of CD is 2.5 meters and the length of CF is 3 meters as shown. So we want to first show that the length of AC, this length here, is 2.5 meters. Sorry, is 1.95 meters. Correct to 2 decimal places. Okay, so we can actually simplify this diagram because we're just working with the base. So if we draw ourselves a rectangle here, well then we can label this C, D, E, F. And we know that CD is 2.5 and CF is 3. And A is the intersection of the diagonals. So A is here. Okay? And we want to find the length AC. Okay, well, what do we know about A? Well, we know that A is halfway along the line CE. Or, yeah, halfway along CE. Because it's in the middle, so it's halfway along the diagonal. And then we can say that, so the length of AC is half the length of CE, since it's halfway along. And now all we need to do is calculate CE. And since this is a rectangle with a right angle here, then we can just look at this triangle here. Let me just do this out. This triangle. And we have a right angle triangle, so we can just think of Pythagoras' theorem, a squared plus b squared equals c squared. And A is CD. B is DE. And C is what we're looking for, CE. Okay, so then we get 2.5 squared plus 3 squared equals CE, the length of CE squared. So the length of CE is the square root of 2.5 squared plus 3 squared, which is 3.905 meters. Okay, so then AC will be half of that. So AC is 1/2 CE, which is 3.905. So AC is 1.952, or to 2 decimal places, 1.95 meters. Now on to part 2. The angle of elevation of B from C is 50 degrees. So that would be this angle here is 50 degrees. Yeah, so as they say, BCA is 50 degrees. And we want to show that AB is 2.3 meters, correct to 1 decimal place. Okay, so again, we can simplify this by, because we're just looking at this triangle. It's the only thing we're looking at here. We're looking at this right angle triangle CAB, where this is 50 degrees, and we know that AC is 1.95 meters. Okay, so now we have a right angle triangle where we know the length of one side, we know one of the angles, and we're looking for this length here, AB. And so we know that, well, how can we relate x and 1.95? Well, we have tan of an angle is equal to the opposite over the adjacent. So tan of 50 is equal to the side opposite that angle, which is just x, over the side adjacent to that angle, which is 1.95. And so now it's easy enough to solve x. If we just multiply both sides by 1.95, we get 1.95 tan of 50 is equal to x, which is equal to 2.32, or to 1 decimal place, 2.3 meters. Now on to part 3, find BC correct to the nearest meter. Okay, so again, we're still using the same triangle as we just were, so if we draw that out again, we have our triangle CAB. We know that AB is 2.3, and we know that AC is 1.95, and so we're looking for BC. So this should be fairly easy. We're dealing with a right angle triangle, so again we can just use Pythagoras' theorem, a squared plus b squared equals c squared, which you should always write down when you're working with a right angle triangle, even though it might not always be what you want to use. But so now we can just let A equal 1.95, the length of AC, B equal 2.3, the length of AB, and C is the length BC, the hypotenuse. Okay, so A squared, 1.95 squared, plus 2.3 squared equals BC squared. And then we can just solve for BC. BC equals the square root of 1.95 squared plus 2.3 squared, which equals 3.015, or to the nearest meter, 3 meters. So BC is approximately 3 meters. Now on to part 4, find the angle BCD correct to the nearest degree. Okay, so, well, what is that angle? So we're looking for the angle BCD. So this angle here. And so, well, let's draw this out. So we have this isosceles triangle. Oops. This isosceles triangle BCD. So this is our B, the apex, C, and D. We know that CD is 2.5, and we know that BC is 3. Okay, and we're looking for this angle BCD. Okay, so, well, it's not a right angle triangle, which makes it difficult. But we actually could make it a right angle triangle. So, since we could make it a right angle triangle, so there's two ways of going about this. We could split this in half, and let's call this H. And then we'd have a right angle triangle here, a right angle triangle here, and we'd just be dealing with this right angle triangle. BHC, where CH is half the length of CD because we split it in half. So this is 1.25, and this is 3. And this is the angle that we're looking for because the angle is still the same. And then we would use, okay, so we have the adjacent of our angle theta, and we have the hypotenuse, so we would use cosine. So cosine of an angle is adjacent over hypotenuse. And so cosine of this angle is equal to 1.25 over 3, the hypotenuse. And so theta, if we use our cosine inverse function, get theta equals cosine inverse of 1.25 over 3, which equals 65.4 degrees, or 65 degrees to the nearest degree. So this would be a perfectly legitimate way of going about it. Theta equals 65, and probably the easiest way of going about it. But you have to think to split the triangle CDB into two right angle triangles, here. So it's a little bit trickier in that sense, but once you notice that, it becomes very easy. But there is another way of doing it. So we do have a way of dealing with right angle triangles. Sorry, we do have a way of dealing with non-right angle triangles. We could use the cosine rule. So whenever you're working with a non-right angle triangle, it may be useful to use the cosine rule. C squared equals a squared plus b squared minus 2ab cos c, where c is the angle opposite the side c. Okay, so in this formula, a would be, well, that would just be, let's say, CD. B would be BC. And C would be BD. And then our angle C is the angle that we're looking for, theta. Okay? So we know what CD is. So A equals CD, which is 2.5. We know that BC is 3. And because this is an isosceles triangle, and you can, because this is an isosceles triangle, well, we can sort of see it, because B is like in the center of, well, because A is in the center and B is directly up from A, BD is the same length as BC. So BD is 3. And this is sort of the tricky thing to realize here. So either of these methods have one sort of tricky step, but after that, they're both pretty okay. So then if we plug that in, we get 3 squared equals 2.5 squared plus 3 squared minus 2 by 2.5 by 3 times cosine of theta. Then these 3 squared will cancel. This 2.5 will cancel. And we get cosine theta equals, sorry, I'll do a few more steps. So then we're left with 0 equals 2.5 minus 6 cosine theta. And then cosine theta equals 2.5 over 6. Or, this is the exact same as 1.25 over 3, which is what we had here. So, as you should, you get the same answer because it's the same angle. They're just two different ways of going about this. So then, of course, theta will be 65 degrees. So it's sort of up to you which is the easier method. I think that the first way of going about it is probably easier. I think it's always preferable to work with right angle triangles if you can, just because we're so much more used to working with them. But you know, using the cosine rule is just as valid. Now on to part 5 of the question. Find the area of glass required to glaze all 4 triangular sides of the pyramid. So just the triangular sides. And give your answer correct to the nearest meter squared. Okay, so we've got to look at what exactly is it that we'll be doing here. Okay, so the triangular sides, so we'll have to do BCD. Actually, no, that's a bad idea. So this triangle. Then we'll have to do the FBC CF, this side. Then this triangle. And then finally the triangle at the back. So those are the 4 sides. And so you might see pretty quickly that the triangle at the front, the triangle we've been just working with, and the triangle at the back, they're the same triangle. They've got the same length base, same length base, and the same length sides here All these sides are the same. So they're the same triangle. So we actually only just have to work with one, and then we can multiply it by 2. And the same deal for this triangle here, the side triangle, and the other side triangle. Again, same base, same length sides, so same area. Okay, so now let's just narrow this down to looking at the two triangles. The triangle that we've been looking at, BCD, and the side triangle BCF, which has a bit of a wider base. But okay, so let's just give this a wider base. Okay, so so we're looking at triangles BCD and BCF. So these are the two triangles we're looking at, and we're trying to find the area of both of these triangles. So what do we want? We want the area of the triangle BCD and the area of the triangle BCF. And then we'll be able to calculate the area of glass needed as 2 times the area of BCD plus 2 times the area of BCF. As we talked about with this diagram here, the area of this triangle is the same as the area of this triangle, so just multiply by 2. And the area of this triangle, the front triangle, is the same as the area of the back triangle. So again, just multiply by 2. Okay, so let's go about calculating these areas. So, well, we're looking at the area of a triangle. So the first thing we should be thinking of is the half the base times the perpendicular height. Okay, so let's just first work with BCD, this triangle BCD. Okay, so half the base, so the base, as we know, is 2.5. We know that the side lengths are 3, and so what would this perpendicular height be? Well, we could go up to our triangle here and to find the height h. And so we would see that, so the base CD, we know that this is 2.5, and the height we can calculate. So the height well, so if we look at this triangle that we've highlighted in yellow here, we can use Pythagoras' theorem to find the length h. So 1.25 squared plus the length squared equals 3 squared, because it's a right angle triangle. And so h equals the square root of 1.25 squared, 3 squared minus 1.25 squared. Equals 2.73. So the perpendicular height is 2.73. And so now we can find the area of BCD. So the area of the top triangle is half the base, so half times 2.5 times the perpendicular height, which is 3.41 meters squared. So that's the area of the top triangle here. Okay, and so now on to the side triangles. The side triangle BCF. So let's now focus on that one. So consider the triangle BCF. And we have the same sort of process to find the area. We know we're going to need the area equals half base times height. And again, we know that this length here, BC, we know that this is 3. We know that BC equals 3, and so BF equals 3 because they're the same length. And we know that FC equals 3, or CF equals 3, because that was given to us in the first part of the question here. And so now we want to calculate this height here. So we can split it into 2 right angle triangles like we did before. And again, we'll have the 1.5 squared plus the height squared is equal to 3 squared. And so then h equals the square root of 3 squared minus 1.5 squared, which is 2.6 meters. Okay, so now we know the base, so the base is 3. The height, the perpendicular height, is 2.6. And so now we can calculate the area. So the area of the triangle BCF is a half times 3 times 2.6, which gives us 3.9 meters squared. Okay, so now we have the area of BCF and we have the area of BCD, and so now we can use our formula. The area of the whole thing that we need is 2 times the area of BCD. So 2 times, so let's say the area of glass needed equals 2 times the area of BCD, which is 3.41, plus 2 times the area of BCF, which is 3.9. And this gives us 14.62 meters squared, or to the nearest meter square, 15 meters squared. So the area of glass needed to glaze the 4 triangles is 15 meters squared. Okay, now on to part B. Another roof lantern in the shape of a pyramid has a square base CDEF. The vertical height AB equals 3 meters, where A is the intersection of the diagonals, so the center of the square, like before. The angle of elevation of B from C is 60 degrees now, it was 50. Find the length of the side of the square base of the lantern. Give your answer in the form square root of A, where A is a natural number. So they're looking for this length CD, which is the same as FC, which is the same as DE, which is the same as EF. Okay, so we want the length of CD, which is the length of CF, which is the length of FE, which is the length of ED. So just any of these will do. It doesn't really make a difference which one we find. They're all equal since it's a square. So what information have they given us? So we know that the angle BCA is 60 degrees, and the length of AB is 3 meters. So we have this angle this is 60, and we have this length, which is 3. So we have quite a bit of information about this triangle BCA. So this triangle, so if this is A, this is B, and this is C, well, we know that this is 60, and this is 3. And so, well, what can we find out? Well, we were able to find out what AC is, for example. We know that tan of our angle, so we know that tan of theta, so we have the opposite when we're looking for the adjacent. So we know that tan of theta is the opposite over the adjacent. So tan of 60 is equal to 3 over the length AC. And then we can find what AC is. So AC is equal to 3 over tan of 60. So AC equals square root of 3. Okay, so we have the square root of 3. We have is the length of AC. And so how does this help us to find any of the lengths of this square? Well, we know when we were trying to find the length of AC before, we tried to find the length of CE because we knew that AC was half of EC, the length of the diagonal. And so if we do that again, we know that this is also EC is also the square root of 3. So now we've shown that CE is equal to 2 root 3. Okay, well, how does that help us? We found the length of the diagonal. It's 2 root 3. How does this help us find the length of the side of the square? Well, we know that the length of this side, let's call it x, is the length of this side. And we know that this is a right angle because it's a square. And so again, we have a right angle. So we should immediately be thinking Pythagoras' theorem. So the hypotenuse here is CE, so which is 2 root 3. And A is x, and B is x. Okay, so if we sub these in, we'll get x squared plus x squared is equal to 2 root 3 squared. So 2x squared equals 12. So x squared equals 6. So x equals the square root of 6. So the side of each square, the sides of the square are square root 6 meters. And that's it done. So identifying what it is we want, these lengths here, writing down the information that they've given us, the angle and the height of B, figuring out, well, using that information, what can we find? We know we can find this length here. We also could have found this length, but we would have pretty quickly realized that it wasn't really helpful. So we would have had AC, and that would have allowed us to then get EC, and then that allows us to find X. So a lot of the time, you might actually not know. So for example, you might not know why finding AC is helpful. And so if you're thinking, well, how does AC get me to the answer? And I actually really don't think that that thought process is helpful. I think that going about these questions, what are they giving you? What can I figure out with what they've given me? And then you take that next step. And now, okay, now I've got AC. What can I figure out with AC? Well, I can figure out CE. Is that helpful? I don't know. It doesn't really matter. And most of the time, you end up just finding your way to the answer, just using the next logical step of the information that they've given you. And I think that this is the best way of going about such a question without getting yourself confused. You know, if you try and figure out, how do I get to the answer straight away, you're just going to get confused. You might end up getting flustered, and that's really not good going into the long questions.